Another question, another problem that is interesting to do is a problem about Newton's second law and torque. For example, if we look at a uniform disk with certain mass, in this case 2.5 kilograms, and radius of 20 centimeters, which is mounted on a fixed horizontal axle, I can run a block attached to a rope that is connected to the disk, and I can ask the following question: what is the acceleration of this block as it is falling down towards the ground? Before we would attack this type of problem using Newton's second law, because we considered pulleys, which is what this disk is essentially, to be massless, and so we didn't have to consider have any considerations about the mass and rotation of the pulley or the disk. But now the disk is not massless, so therefore we have to account for that in the solution of the problem. So here is a drawing of the system of block and disk. Here is the block M. It's hanging by this rope, which is attached to this disk, which again is a pulley. Those two have different masses. The free body diagram with forces indicated on it looks like so. So we have the block here, the force of gravity pulls it down, then there is tension in the rope that pulls up, and then on the side of the disk there is tension in the rope right here, and we will have to think about how we use that to solve the problem at hand. So the first question is to find the acceleration with which the block is falling down, then the angular acceleration of the disk, and also the tension in the rope or in the cord. The one thing that we must consider is the fact that the cord does not slip, and also that there is no friction in the axle. So those two are important conditions in order to be able to apply the second law so that we can solve the problem accurately. So Newton's second law applied to the block states that the tension in the cord minus the weight of the block is equal to the mass of the block times the acceleration with which the block is going to be moving. We have a minus sign here since the positive orientation in the problem is vertically up and the motion is vertically down. So if I rewrite a little bit, I get that MA is equal to mg minus t, which brings the question, how much is t? What is t equal to? We don't know it. So in order to figure out what t is equal to, I'm going to use the definition of torque. So the tension in the rope creates torque with respect to the axis of rotation of the disk. And this torque is equal to the magnitude of the tension force times the radius of the disk. The torque is also defined as the product of the moment of inertia of the disk and the angular acceleration of the disk. So then I can rearrange the terms again and express the tension in terms of the moment of inertia, angular acceleration, and the radius of the disk. The moment of inertia of a uniform disk is equal to the mass times the radius squared divided by 2, and the angular acceleration of the disk will be equal to the tangential acceleration A divided by the radius r. So I will substitute those two in the expression for the tension force. And I get that the tension in the cord is equal to the mass of the disk times the acceleration of motion of the block divided by 2. Now I can substitute this expression in the expression that I got from Newton's second law, right here, and calculate the acceleration of the block. So after substitution, I get that MA is equal to mg minus MA, where m is the mass of the disk, divided by 2. Rearranging the terms gives me an expression for the acceleration. That is that A is equal to twice times the mass of the block times gravitational acceleration, divided by twice the mass of the block plus the mass of the disk. Substituting the values I know for the mass of the block and the mass of the disk in the expression for the acceleration gives me that the acceleration with which the block is falling down is 4.8 meters per second squared. Going back into the expression for the tension force and substituting the mass of the disk and the acceleration of the block, I get 2.5 kilograms times 4.8 meters per second squared divided by 2 is equal to 6 newtons. So that's the magnitude of the tension force. I can also calculate the angular acceleration by substituting the value for the acceleration of the falling block and dividing that by the radius. So that's 4.8 meters per second squared divided by 0.2 meters. That's 24 radians per second squared. So for those types of problems, we have Newton's second law applied for an object that is in some sort of motion, in this case the block, which is falling down. And then we apply the definition for torque for a rotating object in the problem. In this case, that's the disk here. And this definition here for torque allows us to find an expression for an unknown force that also appears in the second law equation for the moving object. So essentially, I'm considering a system of two equations for two unknowns, from which I will isolate one of the unknowns and solve for the other, and then go back and solve for the first unknown.